Okay, so we've got a bunch of trig identities to go through. So let's just get into it. First one, we have 1 minus sine theta times 1 plus sine theta equals cos squared theta. Okay, so sines and coses here should make it a bit easier. Let's start with the left-hand side. Now, this thing looks familiar. It's just the difference of two squares. So we have 1 minus sine squared theta is the left-hand side. Now, this reminds us of one of our Pythag identities. We have sine squared theta plus cos squared theta equals 1. So we can just manipulate that to make cos squared theta equals 1 minus sine squared theta. And this is a common manipulation with this identity. So we have the left-hand side is therefore equal to cos squared theta, which is just our right-hand side. A nice easy one. Our second looks like this. 1 plus tan squared alpha times cos squared alpha is equal to 1. Now, there's a few ways of doing this, but the easiest way is to first notice that 1 plus tan squared alpha is equal to sec squared alpha using one of our Pythagorean identities. So, our left-hand side becomes sec squared alpha times cos squared alpha. Now, we want to try and stick to just sines and cosines, so we can turn that sec squared alpha into 1 over cos squared alpha, because sec is just 1 over cos, times cos squared alpha. But these two cos squared alphas just cancel out. So we're left with 1, which is our right-hand side. Another nice one proved. Our third one looks like this. Sine of A plus cos of A all squared is equal to 1 plus 2 sine A cos A. Now, let's see what we can do with this. Our left-hand side, we can just expand it to get sine squared A plus 2 sine A cos A plus cos squared A. Just expanding a nice square. Now, we're actually almost there. We can see that we've got the 2 sine A cos A, and we just need to turn the sine squared A and the cos squared A into 1. But we have a Pythagorean identity that can already do that. We know that sine squared A plus cos squared A is just equal to 1. So our identity becomes 1 plus 2 sine A cos A, which is equal to our right-hand side. So we're done. Our fourth one is interesting. We have cos squared x minus sine squared x is equal to 1 minus 2 sine squared x. Now this kind of looks like the Pythagorean identity sine squared x plus cos squared x equals 1, but it's a little bit off. We can actually manipulate this one though. We know that cos squared x therefore is going to be equal to 1 minus sine squared x. And it seems like the right thing to do because we only have sine in our right hand side, so we want to get rid of the cos in our left hand side, and this manipulation will help us. So we have left hand side becomes 1 minus sine squared x from our cos squared x minus sine squared x, and combining terms we have 1 minus 2 sine squared x, which again is just our right hand side. So we have another one done. Our fifth one has a whole bunch of ratios. We have tan squared phi, cos squared phi, plus cotan squared phi, sine squared phi equals 1. Now for this one, we just want to get rid of the tan and cotan to turn it into sines and cosines, just to simplify, because dealing with more than two ratios is always tricky. So our left hand side becomes, well, tan is sine over cos, so we have sine squared phi over cos squared phi times the cos squared phi. And cotan is opposite of tan, so it's cos over sine, so we get plus cos squared phi over sine squared phi times our sine squared phi. Now, cos squareds cancel out, sine squareds cancel out, so we're left with sine squared phi plus cos squared phi. But this is just one of our Pythagorean identities, and it just equals 1, which is the right hand side that we were looking for. And we're proved. This next one's a little tricky. We have 3 cos squared theta minus 2 equals 1 minus 3 sine squared theta. And it's a little tricky, but this is just dealing with sine squareds and cosine squareds, which hints that we should be using our basic Pythagorean identity sine squared theta plus cos squared theta equals 1. Or rather, the modification that cos squared theta is going to be 1 minus sine squared theta. Okay, so using this modification, we're going to know that our left hand side, we can turn that 3 cos squared theta into 3 bracket 1 minus sine squared theta minus 2. We can expand the brackets, become 3 minus 3 sine squared theta minus 2. Combine the constant terms, 3 minus 2 is 1, so we get 1 minus 3 sine squared theta. But this is just our right hand side. So again, we've proved another identity. Now for our next one, we have 2 tan squared a minus 1 equals 2 sec squared a minus 3. Now usually we like turning things to sines and cosines, and you can definitely solve it this way, though it's actually going to be a bit longer. What we should be using here is one of our identities that involves the tan and sec, and that one is tan squared a plus 1 is sec squared a. Okay, one that we should really remember because it becomes vitally important later on when we start doing calculus. So, if we manipulate that just slightly, we get tan squared a equals sec squared a minus 1. And this means that for our left hand side we can get rid of the tan and turn it into a sec. So we get 2 bracket sec squared a minus 1 minus 1. We're left with 2 sec squared a minus 2 minus 1. And those two combine to give us 2 sec squared a minus 3, which is just our right hand side. So we're done. Number 8 is going to use some similar skills. We have 1 minus tan squared alpha plus sec squared alpha equals 2. And we know that we should be using our identity tan squared alpha plus 1 equals sec squared alpha. Question is how to do this. So we can just replace the sec squared with tan squared plus 1. So if we try that on our left hand side, we have 1 minus tan squared plus tan squared plus 1. But we see that our tan squareds cancel out, we've got a minus and a plus, and our 1 plus 1 is going to equal 2, which is our right hand side. And we're done again. So, knowing our Pythagorean identities really helps in these cases. Number 9 looks really horrible. We have cosine to the power of 4x, and when we get to the power of 4 that can never be good, plus cos squared x sine squared x equals cos squared x. But all we need to do is actually just use our algebra skills here. We have our left hand side, and the first rule of algebra is to factorize. It's not really the first rule, but it will do here. We can factor out our cos squared x, and we're left with cos squared x and the sine squared x. And suddenly that factorization makes it look a whole lot nicer, because we know that cos squared x plus sine squared x, or sine squared x plus cos squared x, is just equal to 1. That's our basic Pythagorean identity. So we are just left with our cos squared x, which is a whole lot easier than we thought this one was going to be. This is just our right hand side, and we're done. For our final identity, there's actually a whole range of strategies that could work here. It's not a nice problem, or as fast these problems go anyway, but there are a whole number of ways which can solve them. Some of them are quick but not obvious, other ways are obvious but not quick. We're going to just brute force this one with sines and cosines. Okay, and I'll show you at the end a quicker way of doing it. But we have a left-hand side, and if we turn our cotans and secs into sines and cosines, we have cotan, that's cos theta over sine theta, it's the opposite of tan. Bracket, sec is just 1 over cos, so it's 1 over cos squared theta minus 1. Okay, now that bracketed term we want to turn into a single fraction, but we can turn that 1 into a cos squared over cos squared. Why cos squared over cos squared? Because we want to make the denominators the same, turn it into a single fraction. That's what we should always be looking to do in any problem. So we're left with cos theta over sine theta times a fraction which is 1 minus cos squared theta over cos squared theta. Now, we know that sine squared theta plus cos squared theta equals 1, which means that sine squared theta is going to be equal to 1 minus cos squared theta. This means we can turn that second fraction, okay, the first fraction is still cos over sine, and that second fraction becomes sine squared over cos squared. Now, a little bit of cancellation, that cos squared disappears and that cos squared becomes a cos, that sine disappears and that sine squared becomes a sine. So left with sine theta over cos theta. Now, our right hand side is tan theta, which is also sine over cos theta, so we're actually done. Okay. Now, there is another way that we could have done this. I just want to point it out quickly. We know that tan squared theta plus 1 equals sec squared theta. So, we have tan squared equals sec squared theta minus 1. And by turning that bracketed sec squared theta minus 1 into a tan squared theta, we actually could have done this problem in a couple less steps. However, it's not as obvious as just turning everything into cosines and sines. So the question you have to ask yourself is, do you remember all your identities and can you choose the right one to use? And that's the problem with all of these problems. Simplest strategies though, remember all your identities, and worst comes to worst, just change everything into sines and cosines. And be very careful with your algebra.